The stained glass windows in Washington National Cathedral are a sight enjoyed by visitors, particularly on a bright, sunny day. Although the cathedral was built in modern times, it's modeled in the style of 14th century Gothic architecture. Light is a central feature of Gothic architecture, and builders of this period incorporated expansive stained glass windows into cathedrals to bring light into these enormous structures. As the sun's white light streams through the cathedral's windows, it's filtered by the stained glass. Red glass, for example, will only let through red light, and blue glass will only let through blue light. Since the sun contains all the colors of the rainbow, each color of glass is able to transmit a portion of the sun's light. But what would happen if the sun only emitted yellow light and nothing else? If that were the case, then the red, orange, green, blue, and purple pieces of glass would appear black, and only the yellow would glow. But why does this happen? Why do some materials let through different colors of light? And why are materials transparent at all? It all happens at the atomic level. Consider a regular piece of window glass. We know it lets through visible light because we can see it. But most glass will block out ultraviolet light. The difference between visible light and ultraviolet light is the frequency, or the energy of the light. Ultraviolet light has a higher frequency and energy than visible light. When light hits a material, the electrons in the atoms of the material are forced into vibration. These electron vibrations are transmitted to other electrons in the material. Materials such as glass and water allow light to pass through with almost no absorption, and we say these materials are transparent to light. The vibration of electrons in a material is similar to the vibrations of ringing bells and tuning forks. Bells ring at a particular frequency, and tuning forks vibrate at a particular frequency. And so do the electrons of atoms and molecules. Different atoms and molecules have different resonant, or natural frequencies. Electrons in glass have a natural vibration frequency in the ultraviolet range. When the ultraviolet rays in sunlight shine on glass, the electrons are able to hold onto this energy just a bit longer than for visible light, about 100 millionths of a second. During this time, the atom undergoes about 1 million vibrations. It collides with neighboring atoms and transfers absorbed energy as thermal energy. Thus, glass is not transparent to ultraviolet. Glass absorbs ultraviolet. For visible light, the electrons in the glass are forced into vibration, but at a lower amplitude. The atoms or molecules in the glass hold the energy for less time, with less chance of collision with neighboring atoms and molecules. Therefore, less of the energy is transformed into heat. Instead, the energy of vibrating electrons is re-emitted as light. Glass is transparent to all the frequencies of visible light. The frequency of re-emitted light passed from molecule to molecule is identical to the frequency of the original light that produced the vibration. It's the same principle for stained glass. Stained glass lets through a portion of visible light. The electrons in the red glass, for example, absorb all the frequencies of light from the sun except for the red. All stars, including our sun, emit all the colors of the rainbow. But there is a particular color that is most intense for every star. Its peak intensity. The sun's peak intensity is in the yellow-green. As creatures that evolved on planet Earth, our vision is most sensitive at this frequency. The peak intensity of a star hints at its temperature. Hotter stars peak at higher frequencies and higher energies in the blue part of the spectrum, and cooler stars peak at lower frequencies and lower energies in the red part of the spectrum. Therefore, a hot star appears brighter through a piece of blue stained glass than a piece of red stained glass. And the opposite is true for a cool star. Astronomers use this fact to measure the temperatures of stars with their own version of stained glass, colored filters. By comparing the difference of a star's intensity through a blue filter versus a green filter, for example, the star's surface temperature can be determined. The technique of using filters in this manner is called photometry. By taking advantage of the physics of the very small, we can measure the temperatures of enormous stars light years away.